In this session we are going to derive an expression for the difference of specific heats. The molar specific heats at constant pressure and constant volume can be expressed as Cp equals to dou Q by dou T at constant pressure P and Cv is equals to dou Q by dou T at constant volume V. We already know that we can write T into dou S is equals to dou Q, then we can replace the, otherwise we are subtracting Cp minus Cv, that is equals to T into dou S by dou T at pressure P minus dou S by dou T at volume V. Let this be the first equation. Now we are going to take the entropy as a function of V comma T, then the perfect differential of this term can be written as ds is equals to the partial differentiation of these two variables can be written as dou S by dou V at temperature, constant temperature T into dV plus dou S by dou T at constant volume V into dt. Nextly we are going to again differentiate the on both sides with respect to temperature T and taking the constant as variable constant as pressure P, then dou S divided by dou T at constant pressure P is equals to dou S divided by dou V at temperature T, then the differential of this function can be written as dou V by dou T at constant pressure P plus dou S by dou T at volume V will be remain the same, but the differentiation of this function with respect to T at constant pressure P, so this term is going to be equals to 1. Then we are taking this term onto the left hand side, then we can write dou S divided by dou T at pressure P minus dou S divided by dou T at volume V is equals to dou S divided by dou V at temperature T into dou V divided by dou T at pressure P. Let this be the equation number 2. Now we are going to substitute the equation 2 in equation number 1. Then we can write Cp minus Cv is equals to T into the term that is dou S divided by dou V at constant temperature T into dou V divided by dou T at pressure P. So this is, let's say, equation number 3. Now in equation number 3, the first term, that is we can write dou S by dou V at T from the second Maxwell equation as dou P by dou T at V. So then we replace that, then we can write T into dou P by dou T at constant volume V into dou V divided by dou T at constant pressure P. Now for a perfect gas we can write PV is equals to RT. Now we are going to differentiate this equation with respect to firstly P on both sides, then we can write, for example, P is equals to RT by V, then dou P by dou T at constant volume V, then that is equals to, let's say, RT R into R by V into dou T by dou T at pressure P. So this equation, this term will become equals to 1. Then dou P by dou T at volume V can be written as R by V. Similarly, if we are differentiating the function with respect to V and taking pressure as a constant, then we can write dou V divided by dou T at constant pressure P is equals to R divided by P into dou T divided by dou T at constant pressure P. Then we can write this equation as equals to 1. Finally we can write Cp minus Cv equals to, now we are going to substitute the values dou P by dou T at constant volume V as equals to R by V and dou V by dou T at pressure P equals to R by P in this equation. Then we can write Cp minus Cv is equals to T into R by P into R by V. Then we can write for the above equation TR square divided by PV. Since PV equals to RT, then this PV term can be replaced by as TR square divided by RT. Now we are cancelling this all terms here. We are left over with only R. So that means we can write Cp minus Cv is equals to R. So that is nothing but the difference of the specific heats.